Hi, we have a question, which is the venturi meter shown reduce the pipe diameter from 100 mm to a minimum of 50 mm, as shown in the figure there. Calculate the flow rate and the mass flux, assuming ideal condition. So the first step, we need to understand the question. What the question asks. So we need to highlight. Calculate the flow rate and the mass flux. So the mass flux is actually m dot, which is rho q. And the flow rate here refer to q equal to a times velocity. So from this part, we need to list out. Step number 1, list out all the assumption, which is assumption number 1, since we dealing with water, then density is constant. And here, the velocity profile is uniform. And after that, alright, after we have list out all the assumption, step number 2, we need to list what we have in point 1 and point 2. Let's say we consider here point number 1 and point number 2. So point 1 and point 2. What we have at point 1? We have velocity, definitely. And point number 2, we have velocity. Point number 1, we have pressure. And point 2, we have pressure. And point 1, the elevation is the same. Z1 equal to Z2. Z1 equal to Z2. As well as Z2 equal to Z1. So after we have list this out, alright, we need to analyze. This is water flow in the venturi meter. So eventually the flow from initially at the constant cross-sectional area and eventually reduce in area. So the pressure will drop, the velocity will increase. So in order to measure the pressure at 1, we follow this this attached tube, U-tube, alright. This we have the different fluid. This is a mercury, alright, and this is point A and point B. So from here, we need to, step number 3, we need to find, alright, let's take point A equal to point B. Alright, the reason why we equate point A, pressure A equal to pressure B, because we need to find pressure, the relationship of pressure at 1 to pressure at 2. So from here we can equate pressure A, point A is actually equal to pressure at B. Remember, hydrostatic pressure have the same pressure due to elevation. So pressure A same with pressure B. So in order to get the pressure A, alright, this level, right, this level, this height, we need to know this height. For example, this is H1. the H1 refer to 1.2 plus Z. So 1.2 plus Z equal to H1. This, in order to get H1, from this point 1.2 plus Z will get this point. So pressure at point A, definitely there is a pressure at 1. We need to plus pressure, right? Pressure at A shall be pressure 1. There is a pressure here due to hydrostatic pressure plus pressure due to elevation at A, which is plus, right, rho G. This is of water. Remember, density of water. Because we have all this, the water. Rho G of H. The H here is H1, which is 1.2 plus Z. Alright. Equal to pressure at point B. In order to get pressure at point B, definitely pressure at point 2 plus this height. We need to separate this height because we have different fluid region. This height refer to this water fluid. This height refer to mercury fluids. So P2 plus rho G of Z plus rho G of this height of 1.2. Remember, this is density of mercury. And based on this equation, basically we know that there is the relative density of mercury is actually density of mercury divided with density of water. So we can have another equation, the same, or density of mercury times gravity over density of water times gravity. So gravity with gravity we cancel out, will form this equation. And remember that this is rho G refer to gamma. So we can simplify gamma of mercury over gamma of water. And relative density of mercury is basically 13.6. In order, alright, 13.6. So in order to get the gamma for mercury, 13.6 must multiply with gamma of water. Right. So from here, we can, this one, density, alright, this basically, rho G is gamma of mercury. So we can replace this part. Alright, we can actually replace this part with this one. Alright, so here P1, this we expand further. P1 plus rho G 1.2 plus rho GZ equal to pressure 2 plus rho GZ plus gamma of mercury, which is 13.6. 13.6 gamma of water times 1.2. Alright. And we look at here, we have same terms. This term cancel with this term and only left this term. So why don't we rearrange the equation? Make the P to go to the other side and this one go to the other side. Alright, so we rearrange, become P1 minus P2. This is positive, go to the left, minus, equal to 13.6 multiplied with 1.2. Right, so this one 13.6 multiplied with 1.2 gamma of water. Okay, and this one basically the gamma of water as well. So minus 1.2 gamma of water. Right, so after we have done this, we have gamma, we factorize gamma. We got here is 13. This one we can solve. Alright, we can solve. 13.6 multiplied 1.2 minus 1.2. Definitely you will get 15.12 gamma of water, P1 minus P2. So P1 minus P2, move gamma to other side, become division over gamma equal to 15.12. You want to put water, W also okay, no W also okay, because we know that this refer to water. Alright, so next step is this, step number 3. Step number 4 is where we need to apply the energy equation. Right, apply energy equation, which is heat of pump plus velocity squared 1 over 2g plus pressure 1 over gamma plus Z1 equal to heat of turbine plus velocity 2, right, squared over 2g plus pressure 2 over gamma plus Z2 plus heat loss. Since we look at here, this portion is very small, there are no involved of long pipe, so we assume here heat loss is equal to 0. There is no loss, right? Alright. Then we need to simplify the energy equation. Since there is no pump, there is no turbine, and we assume there is no loss, right? We can cancel out this term. And heat due to elevation, Z1 and Z2 is the same. Remember our point 1, Z1 is equal to Z2. So we can cancel. It's not 0. We cancel this one. So we rearrange the equation. Alright. We rearrange the equation. Let here we rearrange. So look at the question asked. Calculate the flow rate. So in order to get the flow rate, we need to find the velocity. Whatever velocity, if we get first velocity 1, we use A1. If you get velocity 2, we use A2. Alright. So we need to get the velocity only. So let's say we shall get the velocity 1. So V1. Okay. V1. Okay. Squared over 2g equal to all this term move to okay, since we have simplified this equation, and then step number 5 is we need to find the correlation of velocity 1 to velocity 2. So by using the continuity equation, we know that the flow rate is fixed, right? Here, alright, the flow rate Q1 is equal to Q2. We can find the correlation of velocity 1 to velocity 2. So Q1 is actually equal to Q2. And in order to get the Q1 velocity volume flow rate, area 1 multiplied with velocity 1 equal to area 2 multiplied with velocity 2. So velocity 2, okay, we try to make it velocity 2 become the subject, so we can cancel out the velocity. We can actually replace velocity 2 with velocity 1. So velocity 2 is actually area 1 over area 2 divided with velocity 1. So area 1, look at here, given that when we look at through the cross-sectional area, it will be like circular. So we apply the area of circle, which is pi d squared over 4. So diameter is 100 mm, convert to SI unit, which is 0.1 millimeter. So area we apply pi diameter 1 squared over 4 over pi d2 squared over 4 multiply with v1. So pi cancel with pi, 4 cancel with 4. We left only d1 over d2. We factorize the power of 2, multiply it v1. So we substitute the value of d1, right? Which is d1 is 100 mm, convert to meter, 0.1 over 50. I think it is 50 mm. Okay, so given here, the diameter here is 50 mm. So convert to SI unit, 0.05. The power of 2 multiply with V1. So V2, we use the calculator, 0.1 divided with 0.05. The power of 2 we got here for velocity 1. Alright. This velocity 2, we need to replace with the equation of energy equation. So V1, we left only step number 6. P1 squared over 2g plus P1 over gamma equal to, alright, equal to V2 squared over 2g plus P2 over gamma, right? Only left at this term. From this part, okay, we need to rearrange this term, make it the V1 minus V2. Why V1 minus V2? Because we can actually replace this one. We can actually make P1 minus P2 as well as this one. Alright, V2 equal to 4 V1. So rearrange, move all this term to the left side, become V1 squared minus V2 squared over 2G plus P1 minus P2 over gamma equal to 0. So try to substitute V2 with what we have discovered. V2 equal to 4V1. So V1 squared minus 4V1 squared over 2G plus P1 minus P2 over gamma we have found previously, which is 15.12. Just replace here with 15. Right, 15.12 equal to 0. So after that, we move this one, right? Okay. Okay. And then we try to solve this equation. V1 minus this one, we try to make sure this 4 to the power of 2 is 16. So V1 squared minus 16 V1 squared equal over 2G plus 15.12 equal to 0. This one we move to other side, become minus. Alright, so this one 15 1, this is 1 minus 16 become negative 15 V1 squared over 2G equal to negative 15.12. Negative, negative we can cancel out. And then 2G we move to other side, become V1 finally is 15.12 multiplied with 2G over with 15 the square root whole. Thus the final answer is 4.45 meter per second. Based on this V1, we can calculate the flow rate. Right, step number 7, flow rate, which is Q equal to A V. If you find 1, use A1 B1. So area 1 is pi d squared over 4 multiplied with velocity 1. So pi, diameter is 100, convert to SI unit 0.1 squared over 4 multiplied with 4.45. Thus the answer here is 0.035 meter per second. This is meter cubic. And in order to get the mass flow rate, is actually the relationship is rho Q. So rho of water is 1000 multiplied with the volume flow rate is 0.035. The final answer is 35 kilogram per second. That is the final answer.